I'm not going to begin with the slides right now. What I want to do is go over a couple of little points on the chapter 20. We should have been finished with chapter 20 on charges and fields already, according to the syllabus, but there are some details that I really do want you to make sure we understand. And partly it's because I disagree a little bit with what the textbook says. In the end of the chapter, he lumps together insulators, dielectrics, and conductors. Now, I think in practice, physicists make a distinction between an insulator and a dielectric because they refer to two different things. And I hope you don't get confused by the fact that the text lumps that together somehow. It doesn't make a very clear distinction between an insulator and a dielectric. See, an insulator it has to do with the conductivity of a material. We haven't really gotten to that, but it's the flow of charge through a material, which relates to the conductivity. So we distinguish two major classes of materials. Insulators, through which free charge does not flow, no flow of charge, which we really haven't gotten yet, and conductors, in which there is a relatively free flow, yes flow of charge. So for example, around the wires in your house, you have insulation. Right? Insulation is to prevent the current from getting out of the wire into your hands as you touch it. So we're referring there to the flow of electricity. Now, the dielectric story is a little bit different. There, what the thing I think we have in mind is not so much the flow of electricity in a path, in a circuit like a river flowing, but rather the polarization. Namely, you have a block of stuff, and you put a field on it, and the material responds, and it polarizes in some fashion. That's different. It's not the real flow of like in a circuit. So that has to do with electrical polarization. And then we classify things within this electrical polarization scheme as a dielectric, paraelectric, and ferroelectric. That was the classification I was trying to give you last time. It's not in the book, but I think it's a very important classification. And I really want you to understand that because we organize materials when we're dealing with their polarization properties, which are important, by this category. So it has to do with the fact, for example, that a dielectric applies to all materials because every material has within it plus and minus charges. So if you put it in an electric field, the electric field will pull the plus charge in one direction and the minus charge in the other direction. And so even if the thing were electrically neutral, the pluses are sitting on top of the minuses to begin with, when you put it on the field, there's a little bit of stretch. Not much, really, because you can figure this out, that in an atom, you have a proton and an electron, and they're very close together. And the field is very, very strong, holding them together. And any field we put on is relatively small compared to that atomic field. So the stretch that we get is usually quite small. So it's a small effect of this sort of dielectric polarization, but it happens to everything. As long as there's plus and minus charges, which everything has, since the whole universe is made of it, you'll get this dielectric effect. But as we said, there are some few materials where they are naturally, because of their structure, the chemical bonding we were talking after class, there's double bonds and what was the other word we used? Empty orbitals or something? What was the word? Lone pairs. Yeah, that's a good chemical word. Lone pairs and all kinds of things which are lone pairs to the rescue. Which distort the thing. So even though a molecule like water would prefer probably to do something like this, if this is the oxygen, if you have the 2+ charges, chances are they would have liked to be as far away from each other as possible. So this would be the natural structure if that was the only force operating. But it's not. You have all these lone pairs and covalent bonds and angle forces and whatnot. So it ends up that the water doesn't do this. It does this. And in so doing, it produces a dipole moment this way. It has to do with the fact that there are other forces besides these charge forces acting. And some molecules are forced into this because of their chemical structure, which overwhelms this tendency here. And then we have the case of, again, this has to do with the polarization material, the charge separation of the charges within a body. We have these ferroelectrics, which have dipolar forces, the dipolar parts, which are spontaneously aligned with each other, at least at some temperature. Somebody raised the question, a very good question, about why, if this is all pluses up here and this is all pluses, well, I can understand why this minus would be attracted here, but there's repulsion here. I read somewhere, following up on that good question, what some people have done, here's a very clever idea. You take water, and you put it in an electric field. Take this, so you put it in an electric field. So ordinarily, you don't get a lot of polarization because the electric field is trying to line them up, but the heat motion is making them jiggle. So you get a little bit of extra polarization. And then what these clever people did, they froze the water. That's a good idea. Freeze the water really hard. So even though it's a little bit aligned, if you freeze the water, you freeze in the little bit of alignment. And if you freeze it low enough, apparently, you can get the whole thing to stay polarized. Then you take the electric field away, and the structure is frozen in. Isn't that cute? I think it's really nice. In fact, I read recently where some people try to freeze water. Look at water can be super cooled below zero, and it stays liquid. But if you freeze the water on a plate which has a little electricity on it, the molecules will line up before they really freeze, and so it changes the freezing point because they're partially lined up by the electric field that you put on. So you can change the freezing point of water by putting it on. It's cute. I mean, you can play games with these things once you know the mechanism. Now, the other thing I wanted you to realize is that the different types of materials react differently. See, the book doesn't make this clear. When does they give you these formulas like this? That there's a torque acting on a dipole, right? I think you did some homework and maybe even the energy. But that only applies if you have a permanent dipole. If you don't have a dipole to start with, you can't put a torque on something that isn't there. So what actually happens in the case of the ordinary dielectric, not a dipole one, it's the field itself that creates the dipole. And there is no torque because if you turn the field, you're creating the dipole parallel to the field every time you turn it. So it isn't as though there's something there like this and you're cranking it around. You're making it with the field. And then when you turn the field, there really isn't a torque. So this torque expression does not work in the case of the induced dipole. So this is the case of the induced dipole. And this formula would not work. I don't know if that's a trick question that they might pull on the MCAT or something, but it doesn't work. What happens is that you get a polarization when you apply the magnetic field and the electric field, and proportional to the electric field, like alpha is just some constant. But again, there is no torque in that case because it isn't as though you have a dipole to work with. Now, these formulas hold in case you do have a permanent dipole, because then you put an electric field and it grabs one end, grabs the other, and we'll try to line the dipole up with respect to the field. Both in the case of the paraelectric, para meaning that they are really loose, and ferro meaning they're locked together. And in that case, the whole big block of aligned dipoles will try to line up with the field. And the other thing that comes from that, now here's, I want to see you guess the answer to this. How about this? How fast can one of these dipoles, these different kinds, react to the electric field? Suppose I had the electric field here, and I change it to here quickly. How fast do you think the situation will adjust to the new field in these three cases? What do you think? This is a kind of physics feeling I'd love you to have. Knowing the mechanisms of these processes, which do you think, for example, would be the fastest? Follow the fastest. Anybody guess? We can vote. It's a democracy. How many think this would be fastest? It's a partial democracy. There is a truth. And how many people think this would go fastest? And this would go fastest? Okay. Why? So those that voted for this, can you give me quickly an answer? Anybody? Yes, sir. That's partly it. Partly it. Any other thoughts? Yes, sir. That's going to getting closer. Any other thoughts? Yes, sir. Electrons have, say louder. Electrons are close to zero mass. That's I think, the key. Question is, when you put it on the field and you change it, the stuff is changing. Now, if you put it on the same field and the thing is light, like the light is an electron having light mass, it'll move faster. Electrons tend to move faster than nuclei, than the whole atom. If you have to move a whole atom, it's hard. You know, it's massive, and the same force, well, good old Newton's law comes to our rescue. F equals ma. So we're trying to accelerate things. That is to say, change their position at least, and that is equal to F over m. So if you have the same force, let's say I put on an electric field, QE, or something, now mass. So if you have a heavy mass, it's going to not accelerate as fast. Exactly what you said, sir. So you'll find, and this is a very good thing for you to know, the rates of things happening go, the electron always goes fastest, because he's the lightest thing in matter. And when you have to move ions, or atoms, or molecules, they're bigger, and the same force is going to not give them as much acceleration. In fact, the speed at which induced polarization can occur is about the speed an electron goes around the atom. Because as the electric field changes, it's going to feel it and follow the thing. Because it's moving that fast, it can adjust. So the speed here is around 10 to the minus 15 seconds, which is around the speed an electron goes around. That makes sense, because this is an electronic motion. Now, how about these guys here? They have to move. There's a whole molecule, like a water molecule. If I change the field from here to here, the whole water molecule has to turn over. And that's cumbersome. And the time for that actually is much longer, about 10 to the minus 11 seconds, turns out. In fact, that's the frequency you put your microwave oven, because you want the electron to go, the molecule to go as fast as you can. And it takes about 10 to the minus 11 seconds, so you try to switch around at that speed. If you go too much faster, it won't follow. See, if it takes 10 to the minus 11 seconds to go like this, if you're going faster, it's just paralyzed, you see. So you don't want to go faster than 10 to the 11 cycles, and you don't want to go slower either. But if you go slower, you could do better by going faster. So that's why your microwave oven works with microwave frequencies around that, 10 to the minus 9, 10 to the minus 10 cycles. And likewise with this, I just looked up, in fact, because here, remember I said for ferroelectric, some people talk about making ferroelectric memories, that you get the polarization up and store information and then switch it. But what's very important is the switching time, because you want to be able to write and read very fast. And some people have made thin film ferroelectrics, which they quote a nanosecond. And you can sort of understand that too, because in this case, what you're doing, you're not just moving one molecule in the field, you're moving a whole block of, this is a physical stuff. It's an oriented, polarized block of material, and you're actually moving that to a different position, so you can see why it'd be much slower. That's the kind of feeling I want you to get. Look at the mechanism, and then you can guess how things are going to work. That's what I wanted to say about this. I think it's a little bit different perspective, but it's more whole than what's in your text. Now, I really must go on to Gauss's law, and what happened here? Screen is blank. Okay, so this is the brief outline. We have the idea of flux lines and electric field lines and flux. Now, I know that this, when you read it, it sounds very puzzling. Let's put it that way, because you're drawing Gaussian surfaces, and you've got this and that and all kinds of stuff. It's really very simple. So open your mind to this. I'm going to give you a very simple view of what this is, and it's going to be pretty accurate. Oh, I'm sorry, I didn't need to go that far. Okay, in a steady condition, if you have a net flow of something, if you see something, look, if you have like a garden hose, and you see water coming out, you know there's a source. And if you make a surface, and there's as much water coming in as going out, there's no source inside. So I got this thing here. Imagine this is a, here's the source is this little button here, right? Okay, now suppose I could know which way the little strands are going, like there's an arrow on them. See, in the electric field, there actually is an arrow. You put a charge there, and it tells the direction. Okay, now if I make a surface cutting through these threads, a bubble, I make like a bubble here, and I count the number of strands going into the bubble, and I count the number of strands going out of the bubble. If the number going in is equal to the number going out, there's no source inside. On the other hand, if I were to draw the bubble including the source, then I have a net amount going out compared to the net going in, right? That's it. That's Gauss's law. If you can count the number of strands, the difference between the number of strands going out and the number of strands going in, it tells you how much source you have inside. That's Gauss's law. It's that simple. Now we have this hideous formulation here, which scares everybody to no end. Well, all it's really saying is exactly that. In other words, if I take the stuff that's coming out, let's call it the electric field, and I have a surface, and I just count all the lines going out of this, in and out of this surface. So I take all the lines, and I count them, going in and out of this surface. There's a bubble, and I take the lines, E, and I take the area that they're coming out, and I try to count all the lines. If I can count all the lines, over the whole thing. Now this is the bubble. So yeah, I mean, think of it this way. This is, take all the E's and the dA's over this bubble. And that will tell you if there's a source inside with this little proportionality constant. So if, for example, if there were a charge in here and I took the bubble, I can take a bubble any shape I want because the lines can't get away. I can take a bubble like that. And you see, the thing like this, there are lines coming out, and there are more going out, if that's a plus charge, than are coming in. So it's different from this case. See, because here, I took a bubble, any old shape, and as many came in as went out. So I can say with confidence that there's no charge, there's no source in here. Voila. Here, I count the lines coming out, and I get a net amount coming out. So I say with confidence there must be a charge hiding in there someplace. Just exactly where, I may not know, but there's definitely got to be a charge inside because I'm reminded, just think of this as a porcupine. And I'm trying to figure out, is a porcupine inside all those quills? It's another way of looking at it. Maybe a little bit overkill here. But if I have, what does a porcupine look like? I don't know. It has feet. It has no tail probably, but it's got all these quills, right? Now, if I make my surface in here, and I get as many quills coming in as going out, I say I haven't caught the porcupine. On the other hand, if I put my surface here like that, I see more quills coming out than coming in, so I got them inside. That's it. There's the source. That's Gauss's law. So we have also the fact that you can have a negative charge. You have, we define that the lines come in. But the same story. If you put the bubble out here, any old shape, you will have, see, because the lines don't end. They just keep going. So where I put the bubble, if the line is going to reach the thing here, the charge, as many will come in as go out. And if I integrate over that surface, there's nobody inside. On the other hand, I could put any old shape here, and the fact that I have more going in than going out tells me that there is a negative charge lurking inside of that thing. Someplace. I don't know where necessarily, but he's in there because there's more going in than going out. That's it. Okay? So but the nice thing is that with that kind of dumb idea, you can do some pretty cute things, clever things. For example, you can solve some hard problems. For example, well, let me just skip quickly over these because this makes it harder than it has to be. These are from the textbooks. All it's really saying is that if you can draw a surface, a closed surface, try to catch every line that's coming out through some space, and you add up the number of lines coming out or in, and if there's a net unbalance, there's somebody inside. First, you have to get the idea of an open and closed surface. You really have to close the surface to catch everybody. That's all. So a closed surface would be one where there's an inside and an outside. That's the only distinction. Like this is not a closed surface because there's no inside and no outside. This is a closed surface because there is an inside and there is an outside. And what we do is we consider the area as a normal vector to the point. It's pointing. We know there's inside and outside. So if there's a normal vector pointing to the outside, we say that's a positive normal. That's an n vector normal. Why don't we put it in here? That might be easy. You think it might be easier. Here's a surface. Why don't I put the vector here? But then why don't I put it here, 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 here? It's a little bit confusing. So it's better to just do it this way. Just convenient. And I say I have a normal vector, and this would be the area of that. And I make it small enough so that it's really perpendicular. Because if I had a curved surface like this, if I put the normal here, this isn't quite a closed surface. But imagine I put on lids. So I do it locally. I have every little square here with a normal to it, and that tells me the area. No big deal. And I just count the number of lines coming out through that little area. And if the lines are parallel to the normal, I could call them positive. If they're opposite to the normal, I call them negative. And I just count. And if I get more coming out than coming in, oh, there's somebody inside. That's it. Okay, so let me skip over this fancy schmancy stuff because it's really kind of confusing, but of course it's a simple idea. We just have an outward going normal, that's the area, and the flux, fancy word, is just this. This is what we call flux. It's sort of like if you can imagine a garden hose, you have a flux. And if you include the hose, there's more going out than coming in. On the other hand, if I include just this, unless it's, there's as many going in as going out. So it's the same story. So this kind of a flux, although there's nothing really moving here. Flux you usually think of as the flux of time, something moving in time, but it's not moving, it's steady. It's like the hairs coming out of that thing. Okay, and then we just say that the flux through a closed surface would be the sum of all the little patches. We just integrate over the whole bubble, and that's the total flux with the little bubble sign here. Okay? Okay, but now we want to do this quantitatively and get this formula here. That is, why, if I catch all the lines, how will it tell me quantitatively how much charge is inside? So we do it for the very simplest case, which is the point charge. And that's what this series of slides is going to do. But you see here, I'm not going to pick any old clumsy shape of bubble. I want to pick a smart way of picking the bubble. And that's my choice. As I said, you can, any bubble at all will catch all the lines. I could have made the bubble that way, or that way. As long as I make the bubble big enough that it encloses the charge, the lines coming out will be the same. So let me be smart and pick a bubble commensurate with the symmetry of the charge I'm dealing with. Now I'm dealing with a point charge Q, and it has spherical symmetry, right? Now symmetry is maybe a confusing idea to some of you. I gave a simple example to one of the students in my office hour. You may appreciate it, I don't know. It comes from an Aesop's fable. You know Aesop's fable, there's a little moral there. And the story is of a donkey. And the donkey is hungry, and he's presented with 2 bales of hay. Exactly the same number of straws, the same hay, placed